Let's wrap up chapter 2.5 and actually sneak in a bit of 2.6 material. Let's talk about the derivative of square root of x. That seems like a simple function. We haven't talked about it before. Our book handles it in chapter 2.6 because that's where it's mathematically the most elegant, but I want us to handle it here at the end of chapter 2.5. So what can we say about the derivative of square root? We haven't really talked about that before, but we do have a power rule. We know that the square root of x is equal to x to the 1/2. And then can we use a power rule on x to the 1/2? Technically at this point we only know that we can use the power rule for integer powers, but it turns out it does work for x to the 1/2. Sorry to spoil chapter 2.6 for you. So we can say x to the 1/2 prime is, well, the 1/2 comes down front, x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. So it's x to the negative half. We can go check that. Graphing. So square root looks something like this. It's a parabola sideways. And then what would we expect the derivative to look like? Well, out here I've got positive slopes, but they're not very positive. So I could put a dot here that's positive but not very positive. Over here I have a more positive slope, so I have a value here that's more positive. Over here I have an even more positive slope, so I have a value that's even more positive. Right here I've got an even more positive slope, so I'm getting that. So ultimately I'm getting a curve kind of like that. Now it's hard to know by eye. Is that like 1 over x, 1 over x squared? The claim is that it's 1/2 x to the minus 1/2, and x to the minus anything by eye looks pretty much like this. So we'd have to go check more formally, but it does end up working out. We could rewrite this. Let's do a little extra box here. So we could rewrite 1/2 x to the negative half as 1/2 1 over x to the half, or 1/2 1 over root x. Some people prefer it that way. I say any of these is good. I often think we might as well leave it with a fractional power. That's kind of the more systematic way to write it often. So, so we'll say rewriting it like any of those is optional. Here's an interesting question. What is f prime at 0? What's the derivative of square root at 0? I asked this in class, and a lot of people say, well, think about it. They're tempted to say it's 0. Is it 0? Well, we know it would be 1/2 0 to the negative 1/2, or 1/2 1 over root 0. What's root 0? Well, that's root 0 is 0, so this would be undefined. So that's interesting. The slope right here is undefined. But another way to think about it is, well, the slope was getting more and more positive as I was moving back toward the origin. So we didn't really say what this red curve here was doing. Let's think about what's f prime at something like 0.0001. That would be 1/2 1 over root 0.0001, which is basically 1/2 times 1 over tiny. I mean, it's not as tiny as 0.001, but what's 1 over tiny? It's basically huge. So as we get closer and closer to the origin, this derivative is getting huger and huger, you could say. So it's essentially going to infinity. So f prime of x, as x goes to 0, is going to infinity. So this is undefined, but it's basically an answer of infinity. So that's kind of interesting that this function, which is a fairly nice function, actually has an infinite slope at the origin. Another way to think of that is, let's think of a parabola. Here's x squared. What's the slope of the tangent line at the origin? It's perfectly flat at the origin, so it has a slope of 0. And then think about square root of x, it's basically a sideways parabola. So it's a parabola flipped around the y equals x line. So if the tangent line has a slope of 0, if it's perfectly flat left to right here, it must be perfectly vertical there. So that's another way of thinking about it. All right, let's practice this derivatives with fractional powers thing. Let's try something like f of x equals root 9 squared minus x squared. It's not a bad idea to draw a quick picture of that. That is basically a semicircle with radius 9. So go ahead and take the derivative of that. What do you think? Well, I often find with square roots that it's nicer to express them as fractional powers. So I could think of this as 9 squared minus x squared to the 1/2. So then the derivative, well, I've got my inner stuff and my outer is stuff to the 1/2. Let me separate that. So it would be 1/2 inner stuff to the negative 1/2 times the derivative of the inner stuff. So 1 over 2, 9 squared minus x squared to the negative 1/2. And then what's the derivative of 9 squared minus x squared? Well, it's tempting to put the 2 in front of the 9 and say it's 2 times 9 to the 1, but 9 squared is just a constant. It's just 81. Its derivative is 0. And then derivative of x squared is 2x. And that's our derivative. We could go check it on Desmos if you want. We could try to sketch the derivative graph here real quick, just to say what should we expect to see. Well, here we've got a flat tangent line, so we'd have a slope of 0 there. Over here, we'd have a very, very steep tangent line, and in fact, right at the last point of the circle there, that would be an infinitely steep tangent line. And over here, a negative slope. Over here, we'd have an infinitely steep tangent line, but right near positive slopes. So we should see something that does that. And I know that looks like negative tangent, but it turns out it's not. It's this expression. Let's try one other quick fractional power kind of problem. Let's say f of x equals 1 over root x. What's f prime? Well, what do you think? We could use the quotient rule because I have a variable thing in the denominator, but I'd rather write it as x to the negative 1/2. So now can you see how to take the derivative of it? The derivative would be negative 1/2, the power comes down in front, times x to the negative 1/2 minus 1. So that's negative 1/2 x to the negative 3/2. If you don't like working with fractions like positive 1/2, negative 1/2, and negative 3/2, it's fine with me if you want to work with 0.5, negative 0.5, negative 1.5, sometimes positive 1.5, etc. Either way is fine with me. One other quick thing, just to clarify, when we're doing our evaluations on some problems, we want to graph f and f prime. So we'd end up with a graph like we just did here, like maybe here's f, and f prime ends up doing this, and that's good. So those are on the problems where we don't have a tangent line going on. On tangent line problems, I think it's best to graph, let's see if I can spell graph, f and the tangent line, not f prime. So if we had the same thing, all right, say here's the tangent line I got, and hopefully they would meet right where I expected them to meet. If I also had f prime on this graph, I would just get confused about which curve the tangent line should be touching and everything. So if your tangent line ends up not working out, if it's not tangent or it doesn't touch the curve or something, then maybe it's not a bad idea to go graph f prime like you would over here, both the expression you got for f prime and what Desmos gives you for f prime to check that your derivative function is correct. And in that case, I would temporarily not show the tangent line. Go back to kind of this situation, make sure your function, your derivative is correct, and then once you have it correct and you've reinvented or redone the tangent line, then go back to this kind of graph.